Okay, AP Physics C, Introduction to Rotational Kinematics. Are you ready? All right, so last year we talked about centripetal motion, right? Something moving in a circle, right? Some mass, let's say, moving in a circle with some speed, right? And it had a centripetal acceleration, an acceleration directed towards the center of the circular path it's in. Well, this year we call this not centripetal acceleration, we call it radial acceleration, the acceleration directed along the radius of the motion. And rather than just calling this V, we call it the tangential velocity, VT sometimes we call it. Now last year we knew that the radial acceleration or centripetal acceleration is equal to the tangential velocity over r. It looked like this last year, right? AC equals v squared over r. Well, we're going to call it the radial acceleration and the tangential velocity because it turns out this year we might also have a tangential acceleration and we also might have a radial velocity, meaning the radius of this thing is changing. All right, so this is two-dimensional motion, right? It's moving in an XY plane. Or you could think of it in a different way. It's moving in an XY plane, yes. Or you could think of it moving in a what's called a polar plane, where the position is considered a combination of the radius of the object and the angle it's at, theta. So these are the two dimensions of its position, its radius and its angle. So we have a radial component and an angular component. And that's a polar coordinate. It's kind of cool to learn about that. So it's two-dimensional, right? Radius, theta, and if it was three-dimensional, we'd have a z-axis, kind of like something moving in a cylindrical shell, maybe. So what the heck does this mean? Well, let's talk about something going around in a circle really quick, and then the kinematic variables we use. So let's talk about just like a turntable spinning, right? Well, what's its velocity? Or a particle at the edge of the turntable going around in a circle. What's its velocity? Well, it's got some tangential speed. But what happens if you speed that up, right? Vt. It has an AT. Well, that means its rotation rate is increasing or decreasing. That'd be caused by a force. In this case, it's going to be a torque. And the units on these are meters per second, right? That's like the speed of a particle at the outer edge of this turntable is moving at 10 meters per second. Well, that's cool, but what about everything else in the turntable? What about all the other particles? Turns out we will track rotational motion in terms of what we call rotational or angular position, velocity, and acceleration. All right, we're gonna have a rotational or angular position, velocity, and acceleration. And I'm just gonna give you these symbols right away. So, angular position is theta, angular velocity is omega, angular acceleration is alpha. All right, the units of these, well, this can be radians per second, and radians per second squared. Or it could be degrees per second, and degrees per second squared. So the object's rotational position depends on the angle it's turned, basically. And it's like in snowboarding or skateboarding with you a 1080, right? It keeps going beyond 360. You don't start back at zero like in math. You keeping track. So if something rotates through an angle of 3,600 degrees, then it's rotated around 10 times, right? So it's a different way of thinking of something rotating, right? Its angle it's turned through, the rate of change of the angle, and the rate of change of the angle's rate of change. All right. And what's kind of cool about this is all the usual kinematic equations apply to this. So anytime you have a kinematic equation, for instance, average velocity equals displacement over time. Well, average angular velocity equals angular displacement over time. If, for instance, I don't know, delta x equals 1/2 at squared plus v initial t, well then also delta theta equals 1/2 alpha t squared plus omega, that should be v naught, omega naught t. And it all works that way because of the calculus, right? It all follows a constant acceleration pattern, right? Rather than saying this, I could say angular velocity is defined as d theta dt, and I could say alpha is d omega dt. All right, so then I could have a function if omega equals alpha t plus omega naught, right? And if it's a constant acceleration, then I could take the integral and I get El Grande. I take the derivative of this and I get the definition of alpha, right? So anyway, you're going to get into this with the worksheet, right? And kind of build that concept through worksheet 3. We'll kind of come to an understanding of what those variables mean. There isn't, you got to understand when you have, let's say, a disk rotating, right? Every particle of that disk has the same omega, alpha, and theta that it's turned through. At least every particle along, a certain radius. Like, doesn't matter what the radius is. Everything's rotating in a disk at the same rate. You've seen this before. RPMs are revolutions per minute, right? So 1 rev per minute is equal to, well, I'm going to do some dimensional analysis here. 1 rev per minute. This is the old chemistry technique, right? Stoichiometry, where you cancel out stuff. So there's 1 minute per 60 seconds, and there's, I don't know, 2 pi, or I'll say under degrees for now, 360 degrees per revolution, or rotations, whatever you want to say. So what happens here is the units cancel out, rev, min, and we end with degrees per second. So 1 revolution per minute, which, you may have seen before, is 360 divided by 60, is about 6. About 6 degrees per second. 1 revolution per minute, that's pretty darn slow, 6 degrees per second. So you've seen angular velocity anytime you've seen revolutions per minute, RPMs, in a car, turntable, anything. All right, so I'm going to leave it at that for now, just to kind of get your brain going on it. Short little video. You're going to plug away at that worksheet 3, problems 1 and 2, see if you can kind of figure your way through them. I think you'll do well with it. All right, so be good, have fun, talk to you later.